So this is the 20th session on rigid body kinematics. So in this video also I will discuss some more numericals on pure rolling. Okay. This is in continuation of the 19th video. Fine. So if you don't know the theory of pure rolling, then you must first refer to the previous videos and then you must come to this one. Okay. Fine. So I'll take up some more problems on rigid body kinematics. See, one thing I'd like to make it very clear that the videos which I'm making on this mechanics, physics, they are all cover the entire chapter thoroughly. It's a complete theory plus numerical, everything is in the videos. Okay, so if you go through them properly, you don't have to go anywhere else. You don't have to go to any other coaching institute, nor do you have to go to any other online platform. You simply go through the videos and then solve questions from whatever source you have. Okay, so this I'm making it very clear. Fine. So I'll write down the question. So I'll write down the main part of the question. Consider the diagram below in which all the details are given. Alright. So I draw the diagram. This is a fixed horizontal surface. This is a fixed pulley. This is a double cylinder. Here there is a hanging block. This is a massless inextensible string. A block is hanging here. This is a double cylinder. C is the center. R is the inner radius. 4R is the outer radius. This is an inextensible string. This block is moving downward at a certain instant at a speed v with respect to ground. This is a double cylinder of center C and inner radius R and outer radius 4R. Here it's undergoing pure rolling. And the cylinder is, this string is folded on the inner cylinder. Here there is a condition for no slip, which will be written as NS. Okay. As the block moves downward, the cylinder also moves rightward. And here there is no slip, and here also there is pure rolling. Okay. And this double cylinder is a single rigid body. Fine. And center C moves at a speed Vc with respect to ground. And because it is undergoing pure rolling over the fixed surface and center is moving rightward, so for pure rolling here, angular speed of the double cylinder should be omega in same clockwise sense. Then only you can undergo pure rolling here. Okay, fine. Now question is to find Vc in terms of V. To find Vc in terms of V is the question. Fine, alright. And it is specified in the question that center C is moving rightward at some speed Vc with respect to ground, and block is moving downward at some speed V with respect to ground at that moment. Now we have to find Vc in terms of V. Okay, fine. See, first I'll calculate Vc, okay. So here there is no slip, here it is pure rolling. Pure rolling is also a type of no slip, this you must know. Pure rolling is also a type of no slip. Pure rolling is also a type of what? No slip. So what do we do now? What we do, let D1 be the material point of the inner cylinder which is in contact with the string. Okay, fine. Now this block is moving downward at a speed v. The string is inextensible. This point of string is also moving at a speed v. So this point of the string in contact with D1, that is also moving rightward at a speed v. Since here it is no slip, so this point D1 is also moving at a speed v. Point D1 is also moving at a speed v in rightward direction. This point. Okay, fine. Now we have to find the speed of center C. So what do? We apply SRC for velocity between C and D1. So this is C, this is D1. Okay. Now we apply SRC for velocity between the point C and D1. So SP arrow C, OP arrow D1. Okay. Now we give the velocity of selected point C to the point D1. Velocity of C is VC rightward, so we give VC to D1 in rightward direction. Now we write down the sentence, rotation term. D1 moves in a clockwise circle with C as center and radius r. For that we give omega r in leftward direction. D1 is the velocity of D1 is the vector sum of these two. But velocity of D1 is v rightward. So vector sum of these two should be rightward. So this should be more than this. So velocity of D1 will be equal to Vc minus omega r, that is equal to v. Okay. So Vc is equal to omega r plus v. Now we have to determine Vc in terms of v. This omega has to be removed. Now here the drum is undergoing pure rolling over a fixed surface. So if we apply pure rolling criteria at this point, then Vc should be 4r into omega. If we apply pure rolling condition here, pure rolling condition, as we have been doing in the previous videos also, or here pure rolling, Vc will be omega times radius of this outer cylinder, which is 4r, omega into 4r. So from pure rolling criteria here, on the ground surface, we should have Vc equal to 4 omega r. So omega r becomes Vc by 4. So this omega r is substitute here. So this implies Vc is equal to Vc by 4 plus V. This implies 3 Vc by 4 is equal to V. This implies Vc equal to 4V by 3 is therefore the required answer. Alright. So Vc is just equal to 4V by 3. That is therefore the required answer. So Vc becomes equal to 4V by 3. Fine. This is therefore the required answer. Alright. This error bit, okay. Now one more thing I would like to say. This Vc which we have calculated here by this method SRC, this can also be solved with several other methods also. I'll demonstrate one more method. This can be solved by other method also, alternate method. We can use that section formula method. By using that, section formula method, this is like this. I draw the inner cylinder here, drum here, double cylinder here. This is C, this is D1, and let's call this as D2. So C, D1, D2 are all collinear. So I draw this line here. This is C, this is D1, this is D2. Now center C is moving rightward at a speed Vc. D1 is moving at a speed V in rightward direction. And D2, this point of the drum which is in contact with ground, this is at rest. Point D2 of the cylinder, drum double cylinder, which is in contact with the ground, is at rest. Now this distance is how much? R. And this distance is how much? 4R. So this distance is how much? 3R. Now D1 divides the line CD1 internally in the ratio 1:3. Okay. So lambda is equal to 1 and mu is equal to 3. R by 3R, 1/3. So we apply the section formula for velocity. Vd1 is equal to, this is lambda into Vd2 plus mu into Vd1 by lambda plus mu. Alright. Now lambda times Vd2 is simply 0, lambda into 0 vector, plus mu is simply 3. Okay. Vd1 is simply V by lambda plus mu is 4. This implies Vc is equal to 3V by 4. So if you take the magnitude on both sides, it becomes 3V by 4. This is therefore the required answer to the question by method 2. Okay. By method 2 also we get the same answer as we obtained here. Alright, fine. Oh, I made a calculation mistake here. Oh, it's a calculation mistake. Sorry, here there is a calculation mistake. Vd2 is 0. Vd1 is Vc. Sorry, here it is Vc. And Vd1 is simply V. There was a calculation mistake here. Okay, I'm just rectifying it. Okay, fine. So Vc becomes 4V by 3. If I take the magnitude on both sides, Vc becomes 4V by 3. Which is therefore the required answer. There was a calculation mistake here. I rectified it. Okay. Vd2 is 0. Vd1 is Vd1 is V. Vd1 is V. Vd1 is V. Yes, call it. 3 times Vd1. Vd1 is simply lambda times Vd2 plus mu times Vd. This is Vc. This is Vc. Okay, now it's alright. Okay, fine. And Vd1 is simply V. I just made a calculation mistake, so I rectified it. Fine. So Vd1 is V. V is equal to lambda into 0 plus 3 into Vc by lambda plus mu. So Vc becomes 4V by 3. So Vc is equal to 4V by 3. That is the required answer. Okay. So a section formula method also we can solve it, which I have solved it here. Alright. This I'll grab it now. Alright. Actually, before going ahead, one thing I'd like to explain. This is a common mistake which has been observed. First I'll grab it, okay? See, one thing I would like to make it very clear. Many students have doubt that why should center C move towards right in this case? It should move towards left. There is a common doubt which is observed by many students. Students wrongly assume that center should not move in this way, but it should move in backward direction. Okay? But I would like to say this is not possible because here also it is no slip, here it is pure rolling. Center C would move towards left in this case only when either there is slip at this, here or both. If at both points it is no slip, then center cannot move left, it has to move towards right. So I like to make it clear. Why VC should be in rightward and not leftward. Why VC should be in rightward direction and not in leftward direction? Why? So reason is because here it is no slip, here also it is pure rolling. Is the reason. No slip at D1 and pure rolling on the ground. And pure rolling on the ground. That is the reason. See, I'll explain it, okay? This is just the reason, but I'll explain it. See, it's like this. Let us assume, okay? Let us assume to the contrary, block is moving down at a speed v. Let us assume to the contrary that center C is moving left, if possible let. Now here it is pure rolling, center is moving towards left as we have assumed. For pure rolling, omega should be in this sense, okay? And here its radius is r, this is 4r. Here it is pure rolling. So from pure rolling criteria applied at this point, Vc equal to 4 omega r, omega into 4r, 4 omega r. Now this is the point D1, point of inner cylinder in contact with the string. Alright. Now if we apply SRC between C and D1, then I'll rub it here, okay. So now, see, block is moving at a speed v downward. This string is also moving at speed v downward. So this point of the string is also moving at speed v downward, rightward. Okay, block is moving at a speed v downward. Each point of string is moving in rightward v. From no slip condition here, D1 should also move towards right, because if no slip is here to take place. Now we'll see that we get a contradiction. How is that contradiction? Now we apply SRC for velocity between C and D1. So SP arrow C, OP arrow D1, okay. We draw the line joining C and D1. This is the line joining C and D1. Velocity of C is VC left, so we give VC left. Omega is anti-clockwise, so D1 moves in anti-clockwise circle with center C and radius R. So we give omega R in rightward direction. The resultant of velocity of VD1 is the vector sum of these two. Now VC is equal to 4 omega R. So from this relation, omega R is equal to how much? VC by 4. Omega R is just equal to VC by 4. So this is VC by 4. The resultant of velocity of VD1 should be VC minus VC by, because this is more than this, should be VC by 4 towards left. That means that velocity of this point of this point of string which is in contact with D1, that should also move at leftward speed of 3 VC by 4. But that is a contradiction, because this point of string is moving rightward and not leftward. So here we get a contradiction. Here we get a contradiction. Hence the assumption that center C moves towards left is wrong. So center C should not move towards left. It should move towards right. Okay. This I fully explained. Fine. This I'll rub it. Okay. This I'll rub it. So this was the 20th session on rigid body kinematics. Okay. So I'll close this session here. Next session I'll take some more problems on rigid body kinematics. Okay, for pure rolling condition. So I close it here. Fine.